Test of hypothesis is being discussed. We're going to look at testing a claim about a proportion. When we looked at 8.1, let's just quickly recap what we learned. A statistical hypothesis is an assumption about the population parameter. This conjecture may or may not be true. The null hypothesis symbolized by H0 and the alternative is symbolized by H1. We have three methods. Traditional method, it uses the critical value. P-value method, it compares the p-value with alpha. So in the first method, we compare two numbers. In the second method, we compare two areas. So numbers versus areas. Now, constructing a confidence interval, we have those significance level. Alpha is 0.01, 0.05, 0.1. And depending on whether we are dealing with a one-tailed test and two-tailed test, they could correspond to 99% confidence level or 98% accordingly. For example, for 0.01, we discussed that. And so, again, understand that basically when you have a two-tailed test, that means 99% is snagged in between, and the total area in two tails is 0.01. But if you happen to have a one-tailed test, 98% accordingly 1 minus 2 alpha. And so the procedure, there are 4 steps. By the way, the number of steps that I have outlined here, in some cases it may be more or less, but pretty much this is it. Sometimes the last step, they cut it into 3 steps itself. And it is really 3 steps. So it depends on what text you're dealing with. Number 1, state the null and alternative hypothesis. Number 2, come up with a test statistic. You need to use a formula sheet to come up with that. Then come up with a critical value. You need a table to come up with that. And number 4, you compare steps 2 and 3. And you make a decision. Test statistic ends up being in the critical region. You reject it, otherwise you're done. So we have this idea of critical value, critical regions, so on and so forth. So as you look at the graphs, you have a two-tailed test. That means the critical regions are in the two tails, and the other two are one-tailed tests. One of them is a left-tailed test, one of them is a right-tailed test. So it's in the left-tailed test or a right-tailed test, the critical region accordingly. To discuss various types of errors. Type 1 error, basically when we reject the true null hypothesis. And numerically, it's equal to alpha. Type 2 error, when we fail to reject a false null hypothesis. And numerically, probability of type 2 error is equal to beta. So testing a claim about the proportion, we've already started it. A complete procedure for testing a claim made about the population proportion is discussed here. Number 1, the critical value or the traditional method. We've already seen that in this section. The traditional method for solving hypothesis testing compares z-values. For CV, the critical value, and TS, test statistic. Comparison of two numbers. The second method involves the p-value. In the case of a p-value, the p-value or probability value is the probability of getting a sample statistic such as the mean or a more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true. What does it mean? The p-value method for solving hypothesis testing problem is comparing two areas. What are the two areas? Alpha versus the p-value. So what is the p-value? You look at the test statistic and area to the right or left of it, or times 2, depending upon whether it's one-tailed test or two-tailed test. Finally, we look at confidence interval. In the case of confidence interval, for proportion, they may not be identical because we use a slightly different formula for confidence interval. As you remember, for E, we use p hat and q hat. But for test statistic, we use p and q. That's the reason. So the confidence interval method, because the confidence interval estimate of a population parameter contains the likely value of that parameter, reject the claim that the population parameter has a value that is not included in the confidence interval. The objective is to conduct a formal hypothesis testing of a claim about the population proportion P. We should remember the notation. N represents the sample size, P is the population proportion, and P hat is the sample proportion.
The sample observations are a simple random sample. The conditions for a binomial distribution are satisfied. There is a fixed number of trials. The trials are independent. Each trial has two categories of success and failure. The probability of a success remains the same in all trials. The conditions NP are greater than or equal to 5 and NQ are greater than or equal to 5 are both satisfied, so the binomial distribution of sample proportions can be approximated by a normal distribution with mu equals NP, sigma equals the square root of NPQ.
So in short, the requirements are the same requirements for binomial distribution, where we can approximate it by normal distribution. And what it means is that for a binomial distribution, remember, we basically have two categories. And of course, independency and the probability stays the same and so forth. They are there too. And NP and NQ must be large. How large is large? 5 or larger. And don't forget, in some text, they may say number 10. The way you calculate mu is NP and sigma is square root of NPQ in the case of a binomial distribution. The procedure was discussed previously, so let's quickly look at this procedure. We have the null and alternative hypothesis, H0 and H1, the same thing for the p-value. Then we go with the test statistic. That means depending on what we are testing, we use a different test statistic. In this case, in this section, we are dealing with proportion. So the bottom right has the formula for test statistic. Z is p hat minus p over the square root of pq over n. We do the same thing for the p-value. In the case of step 3, the critical value is compared to test statistic. And if the test statistic is to the right of the critical value, assuming it's a right tail test, to the left of that, if assuming it's a left tail test, then we reject H0, and then we start writing the rest. Now understand, of course, if it's a two-tailed test, it really is on one side that you compare it accordingly. In the case of a p-value, the test statistic creates an area. If it's a right-tailed test, area to the right. If it's a left-tailed test, area to the left of test statistic. And if it's a two-tailed test, whatever side the test statistic is, creates an area. You multiply it by 2. That area is known as the p-value. The area is known as the p-value. Now you compare it to alpha. If it's less than alpha, you reject H0. If it's larger than alpha, you don't. And the procedure contains 3 parts. When you make a decision, your decision is only and always about H0, according to the data. Nothing more, nothing less. Then you start writing. So you reject or don't reject or fail to reject H0. Then you say the claim is true or false. Then you restate the decision. The same thing happens with the p-value.
Both the p-value method and the critical value method use the same standard deviation based on the claim proportion p equal to square root of pq over n, so they are equivalent to each other. The confidence interval method uses an estimated standard deviation based on the sample proportion, square root of p hat times q hat over n. Therefore, it is not equivalent to the p-value and critical value methods, so the confidence interval method could result in a different conclusion. Recommendation: use a confidence interval to estimate the population proportion, but use the p-value method or critical value method for testing a claim about a proportion.
The two methods, critical value method and p-value method, the results are identical. When we use the confidence interval, it may be different. Normally it's not, but it may be. And why would it be different? In the case of a p-value and z-statistic, square root of pq over n. But over here, this is what's used for E. Remember, for confidence interval, we have p hat plus minus e. And e is z alpha over 2 square root of p hat q hat over n. That's why we're using p hat q hat, not p and q. That's what it may be different. So let's revisit the question we did. 1,009 consumers were asked if they are comfortable with having drones deliver their purchases, and 54% of 545 of them responded with no. Use these results to test the claim that most consumers are uncomfortable with drone deliveries. So we're going to quickly revisit that and then we move on with more examples. Number one, as we read the question, what is given? Understand it's a binomial distribution with n being 1009. P is given as 0.5. Q therefore is calculated as 1 minus 0.5, which is again 0.5. You have to look at NP and NQ, make sure they are large. Both are larger than 5. You're fine with that. And now we go with the first step, H0 and H1. H0P is 0.5. H1P is more than half. So use the result to test the claim that most, when we say most consumers, that means larger. And therefore it makes it right tail test. It happened to be the claim aspect. Step 2, we use the top right formula to calculate Z. In order to come up with that, we need P hat. P hat is given as 54%. But if it's not, you calculate it as X over N, and you use it in test statistic formula. P hat minus P over the square root of PQ over N. And that will result in your test statistic, which is 2.55. Now, alpha is 0.05. It's a right tail test. Z ends up being 1.645. And you do the drawing to make a decision. I can't emphasize this enough. You need to do the drawing so you see where your test statistic ends up being in a matter of comparison to your critical value. This number is here. Now, this is precise, but yours might be an approximation. It doesn't matter. The fact is it's in the rejection region. It is larger than your critical value of 1.645. So what is your decision? You are going to reject H0. When you reject H0, then you can do the rest of the writing. If the H0 is out, then H1 is in, the claim is in. So reject H0, the claim is true, and there is sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone deliveries. So that was the method known as traditional method or the critical value method. Okay, they call this the traditional method or the CV, critical value. The p-value method also was discussed. Going back actually to the previous one, I want to make sure the test statistic is 2.55. So you want the area to the right of that. Okay, that's the test statistic value. The area to the right of it is your p-value, and you compare it to alpha. So right now with the critical value, I'm comparing two numbers, the critical value of 1.645 and the test statistic of 2.55. The test statistic is way into the rejection region, and therefore we reject H0. In the case of a p-value, we come up with the area. As you can see, just from this graph, the area for 2.55 to the right is definitely smaller than the area z equals 1.645 to the right or alpha. So that gives you a rejection region again. So the p-value looks at the area to the right of your test statistic because it's a right tail test. So the p-value ends up being 0.0054. And because it's less than alpha of 0.05, you reject H0 and you continue writing exactly the same decision as the previous one. You do write the same steps. Obviously, this is not finished, but I just want to show you the difference in that particular step. Now, let's look at TI calculator. You can use one proportion z-test is called. So you go to stat, test, one proportion z-test, and you either enter data is given, or stats. To do that, you need to put the proportion P, X, and N, and then choose whether it's a right tail test, two tail test, or left tail test. And so when we do that, so you use your calculator. So you go to one proportion z-test. So enter 0.5 for P, 545 for X, 1009 for N, and choose greater than. And then calculation will result in the following. It gives you the test statistic and it gives you the p-value. Most calculation is about the p-value, so it gives you the p-value. Now the p-value is 0.005386238 or 0.0054. Okay, if you do the rounding, obviously technology gives you a much better approximation. Now, as far as the confidence interval is p plus minus e, where e is z alpha over 2 square root of p hat q hat over n. So with that being the case, you do the calculation. Now, do I want to do the calculation here? Not really. Instead, what I want to do is just use the technology to come up with. With that being the case, when we use a TI calculator, okay, we come up with the answer. And so the answer ends up being P between 0.514, 0.566. Here's what I want you to pay attention to. This is extremely important. How do we do the interpretation? Remember, if you go back to the question was asking, use these results to test what? They claim that most consumers are uncomfortable with drone deliveries. Or not, they are testing them. Notice what happens when you look at your confidence interval. The endpoints, both of them, both numbers are larger than 0.5. So the entire range of values in this confidence interval is larger than 0.5, which means we are 90% confident that the limits of 0.514 and 0.566 contain the true value of P. The sample data appear to support the claim that most consumers are uncomfortable with drone deliveries. So we calculate the confidence interval. Because 0.5 is not in between, because both of them are larger, that means majority are uncomfortable. If both of them were less, let's say 0.4 to 0.45, I'm just making it up, then that would be the other way around. So it depends whether it contains 0.5 or not. Because it doesn't contain H0, the value for H0, or in this case, P equals 0.5, you reject H0, P equals 0.5. So here's the technology using the confidence interval method, stat, test, 1, proportion Z interval. We end up with this confidence interval. And again, the only reason we say it may not be identical because look at the formula. The formula uses P hat, Q hat, whereas test statistic uses P and Q for the sake of calculation. That's why they may or may not be different. I want to put them side by side. We're not going to repeat going through this process for long. I just want you to see side by side as far as the question is concerned. First and foremost, you write that. So take a look at the first step. You see the first step, the second step, the third step, and the decision. This is what we did. This is being repeated. Just I want to show you the steps involved for traditional method. Again, we are revisiting the question. Take a look at the p-value. Step 1 is identical. Step 2 is identical. It is step 3 that you got to pay attention to. Traditional method uses numbers. That means it uses the critical value versus the test statistic. P-value method uses area. That means p-value, which is the area to the right in this case of test statistic. Compare it to alpha. If it's less than that, reject. And it happened to be less than that, so you are rejecting H0. Let's go to the next example.
There is a claim that 60% of people are trying to avoid trans fats in their diets. A researcher randomly selected 200 people and found that 128 people stated that they were trying to avoid trans fats in their diets. At alpha equals 0.05, is there enough evidence to reject this claim?
So first and foremost, understand what is given. And so there's a 60% claim. So that means our P, that means 200 is our N. 128 people stated that they were trying to avoid trans fats. That is X. And of course, alpha is given symbolically. So that's the first thing. So you are either trying to avoid it or not. That's a binomial distribution and independency and all of the above. So the very first thing, the given should be straightforward. You're dealing with BD, short for binomial distribution. N is 200, P is 0.6. Q becomes 1 minus that. So Q is not given. We are calculating Q. Alpha is 0.05, X is 128, NP is, and NQ, the product I didn't calculate. They are larger than 5, therefore we can use MD or short for normal distribution. So let's discuss the first step. The first step says H0 and H1. Notice H0, H1, claim, tails, all of the above you have to write. So having said that, let's see what we need to do. H0, we are dealing with a proportion, so P equals 0.6. And again, I can't emphasize this enough. Don't ever use a test statistic for the first step. It's always the population parameter, P, mu, sigma, you name it. So P equals 0.6. Now, what is H1? You got to read the question, okay? So there is a claim that 60% of people are trying to avoid trans fat in their diets. A researcher randomly selected 200 people and found that 128 people stated that they were trying to avoid trans fat. Is there enough evidence to reject this claim? So the claim is not saying that it's less than 60% or larger than 60%. It says it's 60%. So less than 60% and also larger than 60% would really, in essence, become the alternative hypothesis, and that's why for H1P is not equal to 0.6, which makes it a two-tailed test. Now, which one is the claim? The claim, there's a claim that 60% of people are trying to avoid trans fat. So I hope you see how important it is that you pay attention to this very first step. Your H0, P equals 0.6 is your claim. This is your claim, according to the question. Now, the second step involves calculating test statistic. To calculate the test statistic, look at the top formula. To use that, we need P hat first. So we calculate P hat as X over N, or you can reuse that as 128 over 200 and do the math. So the Z-score is P hat, which is 0.64, minus P, which is 0.6, over the square root of PQ over N, 0.6 times 0.4 over 200. And now this is just the simple math you do. And the calculation results in number 1.15. So with that being the case, the third step involves alpha and the critical value. So to come up with the critical value, you need to use the value of alpha. So what I want to do for the third step, I would graph something like that. This is a true tail test, notice. And each tail is 0.05 divided by 2. Because it's a two-tail test, you look up the table and it's one of those common ones. It's plus minus 1.96. So this is negative 1.96. This is positive 1.96. So now, notice what happens as far as the next step is concerned. You just compare the two numbers, 1.15, and we notice that 1.15 is, it's somewhere here. 1.15 is between the two numbers, and of course it's closer to 1.96. It's way into the non-rejection region. This is a non-rejection region. So test statistic is in a non-rejection region. Do not reject H0. When you don't reject H0, then the claim becomes true. So fail to reject H0, the claim is true. There is sufficient evidence to support the claim that 60% of people are trying to avoid trans fat. Just for the sake of argument, if we were to do the p-value, that means this is 115, right? To the right of that, this whole area, and this whole area, you have to look it up, of course, definitely is larger than the area to the right of 1.96. Now, what is the p-value? That area times 2. Why times 2? Because it's a two-tailed test. So if you're comparing it to alpha is wrong, you compare it to half of alpha. Or multiply it by 2, multiply this area by 2 and compare it to. Let's look at the last question.
A study of sleepwalking or nocturnal wandering was described in Neurology magazine, and it included information that 29.2% of 19,136 American adults have sleepwalked. What is the actual number of adults who have sleepwalked? Let's use a 0.05 significance level to test the claim that for the adult population, the proportion of those who have sleepwalked is less than 0.3.
Before we do the test of hypothesis, to answer that question, first let's see what is given. Obviously, we either sleepwalk or we don't. Two outcomes, two categories. So that's a binomial distribution. We have this number and this number. This is n, and this one is p hat, because 29.2% of all, no, 29.2% of those 19,136 adults have sleepwalked. So that's p hat. We want to use a 0.05 significance level. That means alpha is 0.05. So this is alpha. And then the proportion of those who have sleepwalked is less than 0.3. That means we are using 0.3 as p. So this is given. You're dealing with a binomial distribution. N is 19,136. P is 0.3. Therefore, Q becomes 0.7. P hat is 29.2%, which means 0.292. Alpha is 0.05. NP and NQ become large if you do the calculation, so we can use normal distribution. So the very first question, what is the actual number of adults who have sleepwalked? So P hat is 0.292 times 19,136. So first and foremost, to answer that question, you have to come up with N. P hat is lowercase x over lowercase n. And this is dealing with a number of subjects, rounded accordingly. It doesn't get rounded up or down. It just gets rounded. Because it's 0.7, it rounds up. H0 and H1, H0P equals 0.3 and H1P less than 0.3. That is a left tail test. And that happened to be the claim also because we are checking this claim. Step 1, H0P equals 0.3. H1P is less than 0.3. Why is that the claim? Read the question. A 0.05 significance level to test the claim that the adult population, the proportion of those who have sleepwalked is less than 0.3. So that's why. And less means left tail test. The next thing is to use the top formula to come up with test statistic. P hat minus P over the square root of PQ over N. Well, we have all of those. P hat is 0.292 minus P is 0.3 over the square root of 0.3 times 0.7 over 19,136. Doing the math gives us negative 2.41. Now, you need to come up with the critical value. So to come up with the critical value, it's very simple. Alpha is 0.05. So if I were to graph it right here, you said this is a left tail test. So this is the left tail test with alpha of 0.05. You can come up with the Z. And if you recall, this was one of those common ones, negative 1.645. So Z is negative 1.645. What about test statistic? Test statistic is way into rejection region. Negative 2.41 is to the left of this number, which puts it into the rejection region. So this is the graph. Those are the numbers. Negative 2.41 is to the left of negative 1.64, which means it's way into the rejection region. You are going to reject H0. When H0 is rejected, H1 is accepted. That means the claim is accepted. That means the claim is true. Here's the decision. Reject H0. The claim is true. There is sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked. Now, for practice, I want to do quickly the p-value method for this example and the confidence interval. I don't want to go through the process of calculation by hand. I want to show you the idea. If you are going to use the table right here, so we are done with this, the p-value method, you want to find the area to the left of negative 2.41. This area would be the p-value. And of course, before even you look it up, clearly it's less than alpha because alpha starts from the left of negative 1.645 and it goes to negative infinity. So it's p-value, you got to look it up, but it's less than alpha and it gives you the same decision, which is reject H0, and you write step 4, all of it the same. The p-value method, when we do the math as far as technology is concerned, you get this p-value, which is 0.0079, so 0.008, and that is definitely smaller than alpha of 0.05. So left tail test, z is negative 2.41. I showed you in the previous page. The p-value is the area to the left of the test statistic, which is 0.0080 roughly, and you make up the same decision because it's less than alpha of 0.05, negative 2.4. So you have the p-value less than alpha. If it's less than alpha, that means we are way into the rejection region. You just write the last step accordingly, starting with reject H0. Remember, the very first step of your decision, which is rejecting H0 or failing to reject H0, is what comes from the data. So that's what you do, and then you do the right. Finally, the confidence interval, and again, you go through the process and you do confidence interval, and the confidence interval is between 0.28661 and 0.2974. So as you can see, the confidence level says both numbers are less than 0.3. It doesn't contain 0.3. So, and both of them are less than. So you really support the less than part, which was H1 in essence. So you reject H0. P is between 0.2866 and 0.297 if you use the technology. The entire range of values in this confidence interval is less than 0.3. So you're 90% confident that the limits of 0.2866 and 0.2974 contain the true value of P. The sample data appear to support the claim that fewer than 30% of adults have sleepwalked.